Okay, here we are on chapter 2 on linear functions. This is section 2.4, fitting linear models to data. All right, so what we can do is by plotting points, we can see if there's a relationship that exists linearly for a set of data. So looking at this data as a raw table of data, where this top row is our x's and the bottom row is our y's, we can't directly tell if there's any kind of relationship. For all we know, it could have something like this, it could be like this, it could be like this. We don't know. And so plotting points is the easiest way to kind of see if there's a relationship. And so if we do that, 0 minus 22, that would be about right here. And then we have 2, and then we have 1, 2, and then negative 19. And so that would be about there. And we have 4, negative 15. And so that would be in the vicinity of this. Well, and we have 6, negative 11. And so that would be in the vicinity of this. And 8, 5, 6, 7, 8, negative 6. So that'd be 2, 4, 6. And then we have 10, negative 2. That would be about there. Oops. And so now that we see this, that does look fairly linear, okay? And so that's one way we can see if there's a linear relationship existing. Now it says find the best fit by hand. Well, finding the best fit by hand, we have to choose basically 2 points, and then what we have to do is we have to do a linear fit for that. And so that means we're gonna have to find our slope, and we're gonna have to find our intercept, and then we can plot our points from there. So what 2 points do we want to use? Well, if we use this one, that's the intercept, and maybe let's use the one that's furthest away from it, this one. That way we can kind of get an idea with those 2 points. Technically, we could use any of them, but I'm going to use the most extreme ones to get that. So for my slope, remember that's the change in y over the change in x. So if I do the change in y over the change in x, the first one is going to be, that's going to be y2, this is going to be y1, so I'm going to have a negative 2 minus a minus 22 over, and then I have a 10 minus a 0, and this is going to be a plus 22 minus 2, so it's going to be 20 over 10, and that gives me a slope of 2. Okay, well, my intercept is right here, and that's b is equal to a negative 22. So with the slope and an intercept, I can write it in the form y equals mx plus b, which says y equals 2x minus 22. And so that would be my equation of the line for best fit based on just that first and last points we have here. Now, what model will this work for? Well, because I used the endpoints, that's the key here. And I'm going to say that means my domain and my range are going to be based on those endpoints. And so the domain goes from 0 to 10, and our range goes from negative 22 up to a negative 2. Okay, and so that's really the range for this linear equation that I found because I used that first point and that last point. Now, if I had used, say, maybe the middle two, then really my domain and range is going to fit only those two, because out here, it might work for so far, but it won't work all the way. And what that means is we're getting into the next part, which is interpolation versus extrapolation. So interpolation is we're predicting values that were within the domain and range of a data set. And so our data set in this case, the domain and range were from the first point to the last point, from here to here. And so predicting values that are within that data set range, that's called interpolation. And so that's where we know for sure the data should fit. And then we have another thing called extrapolation. Now this is predicting values outside the domain and range of a set. And here we're not sure if the data behaves the same. So we're extrapolating. We're saying, well, If the data continues on, we're saying yes, that'll be the case, but it doesn't always work because there's going to be model breakdowns, and that's going to be the point where the model no longer applies, whether it's going to be, going to the left or going to the right, depending on what it is. So maybe if we would have kept going to the left here, the model might have broke down and it might have started going back up here or something. Or once we hit that point 10 on X for the domain, maybe after that, there's no more data points and it really doesn't have anything. So it breaks down there too. So that's going to be where we have a model breakdown. So we don't know what happens beyond where our data range and domain are. Now we have something called a correlation coefficient, which is an R value. And so that's what we're looking for is R. And it's a value that's between -1 and +1. So when we have R greater than 0, that's going to be a positive relationship. And we have R less than 0, we're going to have a negative relationship. So for R greater than 0, it's going to be something, it's moving up and to the right. Whereas if we have R less than 0, we're having a negative relationship and the line is going down and to the right. Now, the closer to 0 our R value is, the more scattered the data. So if we have R is equal to 0, we'll just say it's equal to 0, then our data just is kind of all over the place and we really don't have anything. It's kind of called a shotgun pattern most of the time in statistics. Now, if we have something closer to the -1 or the +1, that's the better linear fit. And there's not much scatter. And so it's going to be, if it's exactly 1 or exactly -1, it's going to be a perfect line. But if it's just close and we've drawn a line between the data, it might look something like that if it's close to 1 and something like that if it's close to -1. So it's not perfectly right on the line, but if it's close, then that would be very close to the 1 or -1. Now our calculators, if you have the TI-84, we can actually get the R value out as well as the equation of a line for our set of data, but we have to make sure we have something turned on, and this is called the diagnostic on. So let's go to our calculator, and this is the TI-84 plus CE. It works on the TI-84, 84 plus, and then silver, and all of them that are that series. And what you do is you click second, and then you go down to 0, which is called the catalog. Okay, and now what we need to do is we need to go down and look for the D's. And I think if we just hit this one, which has got the D on it, that takes us down to the letters D, and then we can scroll down and we find diagnostic on. Now if our little triangle is right beside that, then we can hit enter. Now it says, do you want to turn diagnostic on? And then hit enter again, and it's done. And now anytime we do any calculations, we'll get that R value out as well as the equation of a line. All right, now some calculators have it turned on automatically, some don't. So this is just in case yours does not have it turned on if you have one. All right, and this one, what we're going to do is we're going to draw our own scatter plot again, but then what we're going to do afterwards is we're going to use a calculator to plot it and then find an equation of the line and so on. But first, we're going to do it by hand to show that we can still do things by hand. And so we need the first point, 1646. So we're going by 2, 4, 6. See, how's this going to be? Halfway, 1, 2, 3, 4. So that would be 10, and that would be 15, 16. And so then we need 46, and this is going to be at 50. And so it's going to be a little bit under that and a little bit over that. So somewhere, now I lost where we're at. That's 50, that's 16, so somewhere in that range there. And then 18 and 50, so that's 16, so 18 is a little under that, but it's right at the 50. And then we have at 20, we have 54, and so that's 55, 54 is about right there probably. And then we have 25 and 55. So 25 and 55 would be about there. And then we have 30, which is going to be right here, and 62, which is going to be just a little bit over. So about there. Okay, and then if we had a nice ruler, we could draw a nice straight line, and from there we could kind of figure out our values. So we've drawn our scatter plot, and then it says, when will the temperature reach 28 degrees Fahrenheit? Well, if we go down here to 28, so here's 30, so 28's about here. So if we go up here, Well, it could be, if we're thinking that's linear like that, it could be about at that point right there. Now, where did my 62 go? And so that's my 28. And where do I think that's at about? Well, maybe about 58. Not sure. That would be my best guess based on our simple graph we've drawn here. And so the 28 degrees Fahrenheit is going to be approximately, and this is going to be 58 seconds. Okay, and again, just a rough estimate. Who knows if I need to move up a little bit or down a little bit, but that's getting us in the ballpark. And then it says, what about 45 degrees Fahrenheit? Well, notice we only go up to 30. So now that means here we're interpolating at 28, but at 45, that's beyond our table. We don't know what's out there. So when we get to this point, that's extrapolation. Okay, so 45 is going to be right here. Now, so it's going to kind of come up here. Who knows? Maybe at that point, oops. Oh, now it disappeared again. 45, so maybe it might be about there. Who knows? That's, again, it's one of those things. It's all eyeball. If you had to draw on a nice line, it might be better. It might be a little higher than that even. Let's see. If I can draw, I'm not going to draw maybe. Yeah, I'd say it's closer to that one maybe. So let's say that that's our example. And so where does that land? Well, here's 70, and here's 74 maybe. So at 45 degrees Fahrenheit, that's approximately 74 seconds. Who knows if we're even in the right ballpark there, but that's what we're going to say is the case. All right, and it could even still be a little low. It could be, yeah, it's hard to say. I don't know, maybe. Let me get a ruler here and try to draw the line because that might help. So if we have that point, well, we're going to be close enough. We'll call it that. Good anyway. All right. So are these interpolations or extrapolations? Oh, well, we already answered that question. So this one is an interpolation. And this is an extrapolation. And again, for the same reason, this is within our data set. This is beyond our data set. Okay, and so now what we want to do is we want to see what this looks like in our calculator. And so we're going to plug those points into our calculator. We're going to do a linear fit, and then we're going to see what we have. So let's go back to our calculator. We've got our diagnostic on. And to do this, we need to go to Stat. We need to go to Edit. And now if you've got data in here, what we need to do is clear that data out. So we arrow up until we hit the L1, and then we hit clear. And then it says, are you sure? Yes. And we go over here, arrow up, hit clear. It says, are you sure? Yes. Now we can type our data. So now we just type our x's and y's. X goes in L1, y goes in L2. So our x's were 16, 18, 20, 25, and 30. And then our y's, we had 46, 50, 54, 55, and 62. Okay. Now we've got the data in. Now we have to do the calculation. So we go back to Stat. We go over to Calc, and now we want this linear regression in the form y equals mx. Instead, that has ax plus b. And so we hit number 4. And our x's are in L1, our y's in L2. So we say, yep, and we just enter, and we just keep going down and then say calculate. And then it gives us our feedback here. Okay, so it says our A is going to be 1.0124, or B is 31.3292 if we round that up, and our R is 0.96017. So it's greater than uh, uh, 0, so it's a positive slope, which is what we assumed. And the cool thing is now we know that it's going to be close to 1, so it's a pretty good line fit. And so while we're here still, I want to use these values. I'm going to go out to 4 decimal places, I think, and just because. And then let's calculate what that 28 and the 45 were. Okay, so we're going to take the 1.0124 times x, which is our 28, and then plus we had 31.32, not, oops, 992. Okay, so that's the fit of the line, and now we're plugging in 28, and so it says we should get 59.67, or yeah, we'll just 59.7. So let's go back here. So that was going to be 28 degrees Fahrenheit is approximately the 59.7 seconds. Okay, and our equation of the line we got out, let's write that is, let's put it here, I guess, y equals 1.0124x plus 31.3292. And when we plugged in 28, then we got this. Now let's plug in 45 and see what we get there. So going back here, now I'm going to go second enter. I'm going to go, oops, back here. I'm going to say now 45 and see what we get. 76.9. And so this one is 76.9 seconds. So our first one, we got pretty close. We had 58 is 50, 60 roughly. The second one, 74, 77. That's not bad, but just looking at a graph and pulling it out. So we had said this one was 40. Oh, did I say do 48 or 45? Oh, that's 45. Okay. Can't read my own writing here. And so it was 45. We said 74. So close to what we get with the actual values, and so that's pretty good. And again, what we've done now is we've done our linear regression, we've got that, and we also had our R was equal to 0.96017, and so it's positive and close to 1. So it's a good fit basically, okay? All right, so now what we're going to do is we're just going to plug in 2 sets of data, one here, and what they want us to do is calculate the regression line and determine the correlation coefficient out to 3 decimal places. So now we're just going to go back to our calculator, and now we're going to go back to the stat mode. We're going to type in all our data that we have, and we'll see what we get out. So edit. Now again, we have to go back up here. We're going to clear that. Go over here, go up, clear that. And now we type in those 2 sets of data. So it had a 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13, if I remember the data right. And then we had 44.8, and then we had 43.1. I'm hoping I'm using the same data, and 38.8, and then 39, and then 38, and then 32.7. Now notice, as this one's going up, this one's going down, so this is probably going to be a negative relationship. So that's kind of a thing to note when you're working on these things, which way the datas are going. And 27 and 25.8. All right, so hopefully we have the right data. Now we hit stat, go over to calc, and we want a linear regression again, so we hit 4. And our x is in 1, y is in 2, and so here's our data, okay? And so let's go write that on our first one. And so we found our equation of the line was y equals a negative 2.0, 2. And then if we're doing to 3 decimal places, we'll call that a 1 times x, and then plus 53.57, and then it's 03, so that would be 0. And our R value was going to be equal to 0.986. Okay. And so, we've got this whole set of data. It looks good. And so we've got our equation of our line. Notice our slope is negative. We said it should probably be negative because it kept going down with increasing that one. And so that's what we see. Now this one, this is going down and this one is going down. So let's see what we get there and see if we get the positive correlation. Okay. All right, so let's go back to stat. We're going to edit. Now we're going to clear that data. We're going to clear that data. And so this one we have 100, 80, 60, 55, 40, and 20. And then if we go over here, we've got 2000, and then 1798, and 1589, and 1580, 1390, and 1202. Hopefully I typed all that right. And so we're going to go in back to stat. We're going to go over to calc, do number 4 for linear regression. Yes, we plugged everything in the same way. And we get the positive relationship, which is what we expected. And so now let's write that over here. And so we have our equation of our line is y equals, and then we had 9.984 and 9.984, and then it was a 4.6, and then so that's going to drop that. And then we had plus 1,000, oops, 1,002.420, because we had 4196, and so that's 6 around the 9 up to a 10, and then that would go to 2. And our R value was 0.999. So much closer to 1 than this one is. And so this is a very, very good fit. So that's a very linear set of data. This is still a linear set of data, but not as good as the second one because that tells us the goodness of fit basically. All right. So for the next exercise, consider the scenario. The profit of a company decreased steadily over a 10-year span. The following ordered pairs show dollars and the number of units sold in hundreds, and the profit in thousands over the 10-year span of numbers of units sold, comma, profit. So a number of units sold, and then profit for a specific recorded years. So we have 1, 2, 3, 4, 5 years here, or 5 specific points in time over that 10-year period. And so we want to use linear regression to determine a function y, where the profit in thousands of dollars depends on the number of units sold in hundreds. Okay. And then we want to predict the profit, when the profit will dip below the $25,000 threshold. All right, so what we need to do is we need to plug those data in to our calculator. So we'll go back to our calculator, and we'll go stat, edit, clear out the 2 sets of data. Okay, so now we add them in. So we had 46, 48, 50, 52, and 54. So by 2s. And this was 250. We had 225, 205, 180, and 165. All right, so now we've got our 2 columns of data in. And so now what we want to do is we want to do the calculation. So we're going to go back to number 4 for linear regression. Yes, 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 calculate. And so this is the equation of our line. Now our value is negative, which we expected because it said it was going down over time. And so let's write this down so we have it in our thing. So this is the regression line that we needed. So we ended up with y equals negative 10.75x plus 742.5. Okay. All right, so this is the number of units sold in hundreds and the profit in thousands. So this is the profit in thousands, and the number of units sold is going to be X. Actually, what am I doing here? This is going to be the profit in thousands, and this is going to be the number of units sold. Okay, so we've got our equation, and so now we're supposed to predict when the profit will dip below the $25,000 threshold. All right, so what we have to do is we have to plug in the 25,000 into our equation. Now remember, these are all converted into, we've changed it from hundreds and thousands to just basically the units. And so we have to convert the 25,000 into what we should have. So this is going to be a negative 10.75x plus 742.5. And we want to, when it dips below, and so basically when it gets less than the $25,000, okay? So once it hits below that, that's going to be below the threshold. And so now we need to solve this inequality because that's what we're looking for. Well, how are we going to do that? Well, there's a couple ways we can do it. We can take the 10.5 over and then take the 25 here, or we could take the 742 here, and then when we divide by the negative, remember to switch the inequality. It doesn't really matter. So let's say negative 742.5. And so then we have then the negative 10.75x. We still have less than, and then we have a negative 742.5 plus our 25. So that's 717.5, and that's negative. So now we divide by the negative 10.75, divide by the negative 10.75. Remember, that changes, so x now is greater than, and we have to plug this into our calculator because I can't do that one in my head. And so that was 717.5 divided by 10.7, oops, 75, and we get 66.74. 4, and so if we go back here, so that's going to be greater than 66.74. And I'm going to leave it out to here because remember, units sold is in hundreds, so that means I'm going to move the decimal 2 places. And if we did one more decimal place, that was another 4, I believe. And so then what we'd have is, it would just round. And so we have to convert this back to hundreds. And so X is greater than 6674 units sold. So when it dips below the profit of that one, we have this here. So it has to be that many units sold to have greater than the $25,000 for a threshold. Okay. All right, and so that's how we first use the data to get the linear model. And then after that, we use the linear model to determine inequality where we have to be greater than that or else we'll be below the $25,000 threshold. And that's all I have for this section.